Welcome to today's class, which is the second class in the chapter about the Fuchsian groups. As I said before, Fuchsian groups will be defined to be the discrete subgroups of PSL2R or even of SL2R. And one of the things I'm going to do is to characterize the discreteness of a subgroup of PSL2R in terms of its action on U, which is by Mobius transformations, i.e. by orientation-preserving isometries of the hyperbolic plane. I'm going to start with a result whose proof is of a rather topological flavor, and which is a little bit involved, but the result itself generalizes some situation in say algebraic topology that allows to construct covering maps or covering spaces or covering functions. Namely, suppose you have a Riemannian manifold X, and that and a subgroup G of the group of Riemannian isometries of X. So let's say gamma instead of G, let's say, and that the action of gamma on X as a subgroup of the isometry group has the following property, that around each point of X there exists a disk. So a disk with respect to the metric, right? I mean, so it's a metric disk for the Riemannian metric we are assuming we have, such that the only element of gamma that has the property that the translate or the image of this disk under that element actually intersects that disk, the only element is the identity, right? So that except for the identity, all the other elements of gamma, when I take the image of my disk under that element, is completely disjoint. It's kind of very far away, let's say, I mean completely disjoint from the disk I'm saying exists. And so assume that this happens for every point in X. This condition is, I mean, it really has the flavor of having certain open sets that you can identify, and then kind of in the orbit space having an open set that can be evenly covered by the function, I mean, kind of by the passage to the quotient, right? I mean, to the orbit space. And so it seems that then the projection to the orbit space is a covering map, right? And roughly speaking, this is kind of a way of producing covering maps. Okay, but see, in particular, for such a subgroup, all the stabilizers have to be trivial, because otherwise, around some point, if the stabilizer is not trivial, then any disk is going to be preserved, but it's not yet, I would have an identity element. So, okay. So one may ask the question, okay, can we allow certain stabilizers to be non-trivial? And if so, can you still get some sort of covering space or not, or something close to a covering space? And the answer is yes. One can allow some some stabilizers to be non-trivial. And then this is one way where one can get to the notion of a ramified cover, or maybe even orbifold cover. And so this sort of weaker condition that maybe doesn't allow you to obtain covering spaces, but maybe something close to them, is the contents of the first theorem of today, or the only theorem of today, because that's the only theorem I'm going to prove today, and it is the following: that if you give me a subgroup of SL2R, the following two conditions are equivalent. First, that for every element of the upper half plane, so I'm already considering that SL2R acts on the upper half plane by modulus transformations, that for every point, the orbit of the action is discrete, so it doesn't accumulate on itself, and for every point, the stabilizer is finite. So I allow non-trivial stabilizers maybe, but I somehow require them to be finite. Okay, and this condition, having discrete orbits and finite stabilizers, is equivalent to this condition that every element of this space where I'm acting has an open neighborhood, such that maybe there's some element different from the identity element with the property of not taking V sufficiently far away, right? I mean, maybe there is some non-identity element of gamma such that the image of V under gamma keeps intersecting V. Okay. Maybe, but there are not many. So only finitely many elements of the subgroup gamma have the property of not moving V very far away. And the condition is that every element of U has such a neighborhood, right? That it's like a sufficiently small neighborhood so that not many elements of gamma have the property of not taking it far away. So most elements of gamma take V very far away, except for finitely many, right, which would be this. And of course, saying sufficiently far away is kind of a very informal way of saying this, which is kind of the real formal condition. Okay, so somehow the condition I said about here, about the identity of gamma being the only element such that when I take the image of this under that element, it intersects this disk. That condition is weakened to, okay, maybe there is some element different from the identity that does that, but the number of elements that do that is finite. Okay, so let's say today's class is about, it consists of the proof of this theorem. Later on, we're going to see that these two conditions are also equivalent to the subgroup gamma being discrete. And we are going to see also that in this theorem, it doesn't matter if we take the subgroup in SL2R, or if we project to PSL2R, that working in SL2R or in PSL2R, in at least in this case of the upper half in the upper half plane, is really irrelevant where in which group one wants to work. But let's prove this theorem. So the proof is going to be, there's going to be a lot of contrapositives in this proof. It would be a good exercise to try to obtain direct proofs not using contrapositive. Contrapositive, counterpositive. Oh, now I hesitate. How you say it in English? Anyway, so take an element in U, and suppose that this is not true, that 2 is not true. So I'm going to show that then 1 is not true, right? I mean, so I'm going to show that if 2 doesn't hold, then it cannot happen simultaneously that the orbit is discrete and the stabilizer is finite, right, for a given element. So take this element, and suppose that for every open set around the point I took, this set is infinite. And the conclusion I'm going to reach is that it cannot happen simultaneously that the orbit is discrete and stabilizer is finite. So, well, the first thing is since that set is infinite, since this set is infinite, I can start considering small disks around W0, and in this way start producing elements of this infinitely many elements of this set. So I'm going to do it in an organized way, using the axiom of choice if necessary. So first of all, consider the hyperbolic disk of radius 1 around W0. Right? So the open hyperbolic disk, right? So I mean, here I'm using this B is for ball and H is for hyperbolic, right? I mean, this is a notation I used before when I spoke about hyperbolic circles versus Euclidean circles. Okay, so consider the open set, which is the unit disk, the hyperbolic unit disk around W0. Okay, so that's an open set. So for that open set, I know that this set is infinite. So in particular, I can pick one element of gamma such that this intersection is not finite. Right? I mean, I can pick infinitely many. So in particular, I can pick this one. Okay, now once I pick this one, then I move to the next ball, and then I move to the next ball, and so on. So for each positive integer n, once I have already picked gamma 1 to gamma n, then I look at the open disk with center W0 and this radius 1 divided by n plus 1. For this open set, I know that this set is infinite, which means that if from gamma I erase, or I kind of pay no attention to the finitely many elements I have already picked so far, there is one element that I can still pick that is not one of them and still has the property, this property. Okay, so here you see in this recursive way, in the recursive step of constructing my sequence recursively, is that I indeed use the fact that this set is infinite. Okay, and a small formal exercise is for you to figure out how it is that in this recursive construction I'm using the axiom of choice. Okay, so now by construction, all of the gammas are different, right? Because in each step, in the recursive step, I make sure that I pick one different from the ones I picked earlier, right? So all of them are pairwise different. And furthermore, since I have this condition, so you see, I mean, if I take the ball but around W0, but let's say of radius 1 divided by n, and I apply gamma n, it intersects that ball in a non-empty set. So there is here some point in the intersection. So the distance between W0 and gamma n of W naught is less than this plus this, right? By the triangle inequality. So this distance is less than 2 divided by n, but you see this automatically tells me that the sequence of gamma n, sorry, and this is gamma n, not Gn. This tells me that the sequence gamma n W naught, which is a sequence of points in U, in the upper half plane, converges to W naught. Okay, but you see it converges. But you see, I mean, first of all, these are all different, these elements. Right? So if the stabilizer of W naught were finite, then you see, then only finitely many of these could be in the stabilizer. So I can chop the sequence, and actually assume that none of them lies in stabilizer. Right? So if the stabilizer is finite, then I can further assume that none of them lies in the stabilizer just by cutting off the beginning of the sequence. Okay, but then this condition tells me none of this is stabilized, none of this is W naught, because none of this belongs to the stabilizer, so none of this is equal to W naught. So this means that this is a sequence that converges to W naught, but without ever becoming constant. Right? So W naught has to be an accumulation point of its orbit. Right? So it cannot happen that this is finite and this is discrete, at least not simultaneously. So we have proved that 1 implies 2 by counterpositive. Okay, now let's show that 2 implies 1. So take any element of U, and so well, I mean, by default, if we are assuming 2, since we are assuming 2, for the point we pick, there is such neighborhood, right? Okay, so there is such neighborhood. But you see, this one obviously contains the stabilizer, right? So if I pick my V so that this is finite, then stabilizer is finite. So that's no problem. The hard part is to see that the orbit is discrete. So now I'm going to assume that it is not discrete, and then of course then contradict my condition. So there's again like a counterpositive, contrapositive. So assume the orbit is not discrete. So it's not discrete, which means that it accumulates in itself, right? So there is some element in the orbit. There is some element in the orbit, which is an accumulation point of the orbit, right? So there is a non-stationary sequence of points in the orbit that converges to it, right? So for every positive integer, there is an element in the orbit that is sufficiently close, but is not the point. It's not the point of accumulation. Okay, but once we have this, see, in this condition, I can apply gamma inverse, and then when I apply gamma inverse, this inequality is preserved, and here you can erase this, right? And this is preserved. So when I apply gamma inverse, I obtain this, right? So this is not Z naught, and belongs to this ball. In particular, you see, since the ball, since for m greater than n, for m greater than n, the ball of radius 1 over m is contained in the ball of radius 1 over n. This, you see, and since the center here is the same, here I also have this for m greater than n. So I mean, so I see that Z0 is the limit of this sequence. Okay, this is going to play a role later on. Okay, but so you see now the thing is, given n, for any given n, I have, well, this point is the image of Z0 under this element. So it's the image of someone here, namely the center, under this element. Right? So of course this one belongs to this one. But I just said that it also belongs to this one. Right? So it's in the intersection. Okay. This is for any given n, right? So for m greater than n, you see here, I mean, here if instead of n you write m, you still have the same, right? But if m is greater than n, you see this ball is contained in this ball, of course, if m is greater than n. So I have this containment. And again, this ball is contained in this ball. Right? So this intersection is contained in this intersection as long as m is greater than n. And notice here is an m, not an n. Okay, but in any case, what I see, you see, what I see is that when I consider this element for m greater than n, this element has the property that the image of Z0 under it belongs here. Right? So for all m greater than n, I have this element contained in the elements in this set consisting of all those g's, such that you see here when I write the gamma m, gamma inverse gamma m, I obtain precisely this. Okay, that is, this is not empty. Okay, but you see, this set has to be infinite. Why? Because, as I said here, this limit, the set Z0 is the limit of all of this, of this sequence, which is not stationary. So this must have a subsequence consisting of it must have an infinite sequence consisting of pairwise different points of view. But if they are all different, pairwise different points of view, since they are the result of applying this element, the corresponding element to the same point Z0, well, the elements of gamma cannot be the same. So that's why it's infinite. It boils down to the fact that this convergence is a non-stationary convergence, and that way I contradicted two. Right? So if the orbit is not discrete, then this fails. Right? And I mean, it's counter positive. The nice thing is that if you see the proofs, the counter positive is actually applied point wisely, right? So anyway, so I mean, in other words, if the orbit of gamma, if the orbit of Z0 is not discrete, then it is for Z0 that the condition fails, right? And conversely, right? I mean, if I mean this, yeah. So if W0 doesn't have a neighborhood satisfying this, then it is for W0 that one cannot have simultaneously the discreteness and finiteness here. Anyway, so these type of actions, namely when that the orbit is discrete and the stabilizer is finite, always, that all stabilizers are finite and all orbits are discrete, it's called properly discontinuous. And maybe to emphasize, maybe I would say properly discontinuous in the weak sense, right? And I would say, if necessary, right? If some confusion arises, I would say that it's proper discontinuity in the weak sense, and the proper discontinuity in the strong sense. I would say that it is when here in 2, this set is always only consists one puts only the identity, or when the stabilizers are all trivial. Anyway, I'm going to be saying that these are properly discontinuous actions. If there's some confusion with the concepts from algebraic topology, then I'm going to say that, or from basic algebraic topology, I'm going to say that the action is properly discontinuous in the weak sense. Okay, and next class, I'm going to see that that these two conditions that we saw today are equivalent to the condition that the subgroup gamma be discrete. Okay, now you see the proofs were very topological. So a good exercise is to see to which extent can I generalize this. Right? I mean, can I generalize it to other spaces? This may be a good exercise. But for today, I think I'm going to just finish the class there.